Okay, the video is recording now. And so in the last lecture, we have some discussions about utilizing the equal vertical deflection criterion or the equal vertical stress criterion to estimate the ESWL values. I am sorry that I have some issues about my writing pen. And with basically you can find out the estimation of the ESWL is related to the maximum value of the sigma z over qs or qd at 3 critical points, as what we define in this figure. The one behind the tire, directly behind the tire, the one at the edges of the tire, and also the one between the center at the center point of the dual tires. So this would be the way for us to estimate the ESWL. We have the Boussinesq theory to do the estimation. We also have the first and Alvin method to calculate the value of ESWL, and usually for the first and Alvin method, the value should be much higher than the one we generated or estimated from the linear model. There will be this would be the estimation of the equivalent single wear load through the equal vertical stress deflection criterion. We also have some other criterions, but before I go to that, we will continue to see another method of the estimation about the ESWL with the equal vertical deflection criterion. But this one is actually only applied for the layered system, which is generally applied for the flexible pavement, where we are considered the surface layer, the base layer, the sub-base layer, and the subgrade layer, and so on. If we consider the layered system, then the properties at different of the soil or the materials at different layer will be very different. The most important criterion that feature of the property of those materials will be the modulus of elasticity, which would be the value.
Excuse me?
Hello?
Yes. Are you sharing your screen? Because I can't see it.
Oh, you cannot see it? Oh, that's weird. No. I'm thinking I'm sharing this one. It's the problem for everyone. Let me reshare it.
Oh, okay.
Okay, can you see it now?
No.
Oh,
maybe I join again.
Yeah, I saw you have the I saw your name in the another meeting. Maybe you hold yourself in another meeting. I
closed the other one, but I can try to rejoin.
Yeah. Probably it's better for you to join again.
Okay.
Yeah. Okay. So I'll continue this kind of methods. So if we are talking about layered system, say that there will be the 2 layers. And as I say that one of the most distinct difference about these 2 layers would be the modulus of elasticity. So we say that E1 and E2. So in that sense, in this situation, we cannot use the method in the previous the equations in the previous methods. Instead, we have to consider the impact or the interaction between these 2 layers. Generally, we're going to use the ratio between these 2 elasticity modulus, E1 over E2, to find out this interaction and to identify how the stress or the deflection is propagated from one layer to another layer. So in this method, for when we consider the layer system, we need to think about 4 variables. The first one is the contact pressure. So we say the contact pressure, the contact radius. And the second one is the thickness. it's where you want to estimate the ESWL. And the third one is the ratio, E1 divided by E2, which will be the ratio of the modulus. And the last one would be the spacing. We say that the center to center distance of the dual tire. So those would be the three variables you have to use to find out the ESWL. Basically, you can identify these four variables and then call the two figures below. These two figures will show the load factor, which would be the L for the vertical axis with respect to the thickness. So the horizontal axis would be the thickness. Z, this is also applied to the figure on the right. So these two figures have some difference. The one on the left shows the relationship of the load with respect to the contact radius of 6 inches. But for the one on the right, it shows the relationship between the load factor and thickness with respect to the contact radius of 16 inches. And for both figures, the spacing are all set as 48 inches. Also, in each figure, you can actually find out multiple lines. Each line will represent one ratio of one modulus ratio, E1 over E2. For example, for this one, it shows the, for the first line, here it shows the ratio of 1. And the second one shows the ratio of 2.5. And you can find out the ratio up to 100. And this also applies to the figure on the right. And we can then use this figure to find out the load factor and a different thickness. And the load factor actually equals to the total load of the tire divided by the ESWL, which will be 2 times PD. PD applied to each tire in the dual tire system. And with that, total load is 2 PD, and the ESWL is PS. So once you know the value of L, you can find out the PS if you are provided with the load to the tire. So you might have the question like this is only, this two figure only gives you the specific situation with spacing of 48 inches with the contact radius of 6 inches or 16 inches. We may need to think about how to extend this one to general situations with the other values of the spacings, the other values of the radius. In this book, Huang, which was written by Huang in 1968, they actually showed the equation for you to find out the estimation of the load factor under the general situation. So for the first, for the load factor, we can find out the load factor from the previous definition. The load factor is 2 PD divided by PS, but we also know that PS actually equal to FD divided by FS times PD. This is the equation we derived from the previous slides. And if you apply this one, the second equation to the first one, you can derive the relationship between the load factor and the factor of the dual tire and single tire, FD and FS. So you can get the equation L equal to 2 times FD divided by FS. So this is equivalent to the to this one, to the load and the ESWL. But for the general case with the other values of the contact radius, the other values of the center to center distance, we have another equation to convert them to the standard figures and then find out the load factor. Assuming that we are provided with the center to center spacing SD, the thickness H, and the contact radius A. Then we can convert everything to the or find out the equivalent value of the thickness, or we say that the modified thickness H1 prime and the modified radius of A prime at the at SD equal to 48 inches. So we will convert everything to the standard value. So with that, the modified radius A prime equal to 48 divided by SD times A, and the thickness H1 prime equal to 48 divided by SD times H1. So this is the way for you to revise or modify the thickness and the contact radius. And then you're gonna use the H1 prime as the thickness and find out the loading factor at the L1 and L2. L1 is the figure from the left, where the contact radius A equal to 6 inches. And L2 comes from the figure on the right with the contact radius of 16 inches. And once you have the value of L1 and L2, you can then call this equation to find out the load factor. So L equal to L1 minus L2 times A prime minus 6 divided by 10. And with that, you can then estimate the, because this one equals to 2 times PD divided by PS. You can then find out the value of PS, which will just be the ESWL. So this is the way for us to calculate the equivalent single well load with respect to the layered system. And let me show you one example to see how we can do this, use this knowledge to find out the value. So here we are considering the 2-layer system. We want to find out the ESWL with the modulus ratio of 1 and 25. And in this example, we know the load applied to each tile is 4,500 pounds. So we have PD equal to 4,500, and then 2 PD will definitely be 9,000 pounds. And also for the distance, for the spacing between the 2 tiles, SD, which will be distance from the same one tile to the other one, that will be 13.5 inches. So this is SD. And the thickness that we're going to consider is 13.5 inches. So we have H1 equal to 13.5 inches. And also we know the width of the tile or each tile is this is the width of each tile, and the half width is 4.5 inches, which means that the radius of the contact area is 2.5 inches. So those would be all the information we need to use for the estimation of the ESWL. And now let's go to see the solution. So we have SD. SD is 13.5 inches. We have A equal to 4.5. We have H1 equal to 13.5. And the first thing we need to do is like we have to find out the revised or modified contact radius and the thickness at the spacing of 48 inches. So A prime will be SD, the 48 divided by SD times A. In this case, we have SD is 13.5, A is 4.5. So it gives you the value as just 16 inches. And the H1 prime will be 48 divided by SD times H1. So it's 48 divided by 13.5 times 13.5. So that is 48 inches. And now for the first case, E1 divided by E2 equal to 1. We know the value of A prime and H1 prime. Then we also know the ratio, modulus ratio is 1. Then we have to go back to the figure, to this figure, to find out the value of the value of the loading factor. So for the figure on the left and the figure on the right, we need to find out the thickness, the modified thickness is 48 inches, and this would be the part with the 48 inches. And we have to choose the line with E1 over E2 equal to 1. So that would be the value. That will be the value around this point. And if we go to check the value, this is around 1.22. And you can also go to check the value on the other side for the A equal to 6 inches. This should be, still you need to choose the line with E1 over E2 equal to 1. And the value should be someplace here. And you can find out the value around 1.24. So this is the L1 and this is L2. And then you have to recall this equation to find out the load factor. So we have L1 equal to 1.24, L2 equal to 1.22, and then recall the equation L equal to L1, L1 minus L1 minus L2 times let me just recall this equation. A prime minus 6 divided by 10. This will give you the result as 1.22. So with that, we can then find out the value of ESWL. Just the BPS. That will equals to 2 times PD divided by L. So we have PD is 4500, L is 1.22, and it gives you the result as 7,380 pounds. So this is the first one. And you can go to the second one for E1. The modulus ratio is 25. The procedure will be exactly the same. The only difference is the line you're going to choose. You're going to need to choose the line with E1 divided by E2 equal to 25. So this would be this line. And similarly for the figure on the left. And by doing the similar process, you can find out the value of L1, L equal to 1.06. If we do the similar procedure in the first one. And then you can find out the ESWL as 9,000 divided by 1.06. That is 8490 pounds. Generally, you can find out the relationship between the modulus ratio and the ESW. Usually, if the modulus ratio increase, you will also observe the increase of the equivalent single wear load. So this is the trend between these two variables. So that's for the equal vertical deflection criterion with respect to the layered system. We also have some other criterions. The next one is the equal tensile strain criterion. So we assume that the tensile strength at the bottom of the first layer, the top layer under the single wheel load, will be the same to the tensile strength at the bottom of the first layer with the dual or tandem wheel. So the tensile strength with a single wheel could be estimated by this equation, E equal to QS divided by E1 times FE, and the tensile strength at the with the tandem wheel is estimated with E equal to C times QD. C is in a constant value divided by E1 times FE. So here is the FE is in FE as a strain factor as a constant value, and C is a conversion factor. It's also a constant, and we have to make sure that E1 these two, say that E1 and E2 will be the same. So if we go to check these two equations, E1 equal to E2, you can intuitively find out the relationship as QS equal to C times QD. And as we know that QS is just the equivalent single wheel load, so we can say that PS is also equal to C times QD based on the assumption that the contact radius is the same. So this is the criterion with the equal tensile strength. The model will be much simpler. PS is just proportional to the value of PD. And we also have another criterion, which is called the equal contact pressure criterion. So it indicates that the contact pressure from the single wheel and dual wheel will be the same. So this would be the assumption from this criterion, and we can actually estimate the interface deflection from the single and the dual wheels with these two equations. So the contact pressure Q here represents the Q is the contact pressure, and the AS is the radius. It's the radius of the single wheel tire. And AD will be the radius of the tandem wheel tire. And of course, we have the parameters, the factors for the single wheel and dual wheel. And with that, we can find out the based on the same interface deflection caused by the single wheel and the dual wheel with omega s equal to omega d, we can find out the value of PS, the relationship between the PS and PD. So the this one shows the this equation shows the relationship. Basically, PS equal to FD times FS square times PD. It's a little bit different from the one we previously obtained. Well, previously we have the from the equal vertical deflection criterion, we have PS equal to FD times FS times PD. There's a little bit different. This is from the vertical stress or the vertical deflection criterion. So that's the contact pressure criterion. You just need to know that we have this kind of criterion. And the last one is the equal contact radius. We assume that the radius of the contact area will be the same. And in this kind of criterion, we will, instead of using the equivalent single wheel load, we're going to use the equivalent single axial radius to represent the load from the weak traffic. So with that, we have the we can find out the contact equivalent single axial radius with respect to the specific radius that you want to estimate. And in this equation, A is the contact radius of the of each of the dual tile, and S is the center-to-center spacing between the radius between the dual tiles. And with this contact radius, we can then apply the same thing, the interface, estimate the interface deflection, and make sure that the interface deflection from the single wheel and dual wheel will be the same, and then estimate the equivalent vehicle, single wheel load. So in this class, the first criterion is the most important, and also it's very common. It's commonly applied. The last three will be considered as some additional knowledge you should know about the representation or the estimation of the wheel load. So that's the first method for us to identify the traffic load with the fixed traffic, and it only applies at some specific regions where the traffic volumes won't change a lot. The percentage of the trucks and also the loadings of the truck will be similar over the days. But in reality, this is not the common case. In reality, we usually need to think about the varying traffic volumes over the day and uneven distribution of the truck load and different portions of different type of the truck traffic on the road. With that, we have to think about the how to estimate the the traffic load with the fixed vehicle method. This will go to the next one, the next lecture. Well, we need to think about the or define a new variable, which is called the equivalent single axial load, ESWL. This is the most common criterion or the variable that we're going to use to measure the traffic. First of all, I'll give you a brief definition about the equivalent single axial load. Basically, the ESWL represent the equivalent single axial load, and it will be the summation of the equivalent 80 kilonewton, or we say that 18,000 pounds single axial load to measure the mixed traffic for the pavement design. Here we say that we choose the value 80 kilonewton or 18,000 pounds to represent the standard single axial load. This is one empirical value that we obtained from the real world. This is one example. The figure here shows one example about the single axial with the 18 kilonewton, and this one is considered to be in the dual tile, and we will convert all the other type of the tiles, all the type of combinations about tiles into this standard load. And the reasons like in reality, there will be different type of the vehicles like the passenger cars and the trucks. Their impact about the pavement structures will be very different. So if we just summarize their load, like for the passenger car, their load is 10 kilonewton, but for the truck is 80 kilonewton. But their impact to the pavement structure will be very different. They will not be in a linear relationship. You need to find out a way to convert the damage caused by these passenger cars to the damage caused by the truck, to equivalent to the damage caused by truck. For example, like for the passenger cars with 10 kilonewton, the damage the factor might be only 0.1, even but for the a truck with 80 kilonewton, that will be represent the factor of 1, but for the 10 kilonewton or the passenger car, it's not necessary to be something around 0.1 or 0.15. It could be some value even smaller, like 0.05 or 0.04, something like that. So we will try to identify the damage caused by different type of the vehicles with different loads, and then using the damage to represent the load of the traffic. So they should it should represent the equivalent damage for the pavement structure. So the way for us to measure the damage from the different load of the vehicles or the different load of traffic is called the equivalent axial load factor, EALF. And this one defines the damage per pass to the pavement by an axle in question related to the damage per pass of the standard axle. So if we have the passenger car with a 10 kilonewton load, it was equivalent to 0.005 damage from the standard axle load. The pavement design for the modern design method, most of them will consider the traffic with the pass of the standard axle load during the design period. That will be the ESWL. And generally, ESWL will equal to the summation of Fi times Ni in this equation. M is the number of the axle load groups. You can categorize the vehicles into multiple groups, like small cars, two-wheel, single-wheel trucks, dual-wheel trucks, and tandem-wheel trucks, and so on. So you have multiple groups. And Fi represents the equivalent axle load factor for the ICE axle load group. And N represents the number of the pass of the ICE load group during the design period. So in here, N is related to how many of the vehicles it's moving on the pavement on the pavement structure during the design life. Fi represents the loading factor. What's the damage of the each group, with each pass to the pavement structure, and obviously we have to pay more attention about how we can calculate the EALF. Usually the value of the equivalent axle load factor is related to the type of the pavement, the thickness or the structural capacity of the pavement, the terminal conditions at the pavement failure. Those would be the concept related to the pavement design. We will go through these variables later in the when we are talking about the design of the flexible pavement and the rigid pavement. Generally, we have the one equation from the AASHTO to estimate the load factor. So this is called the AASHTO equivalent factor equation. It's a stochastic model where it assumes that the log of WTS divided by WT18. Here, this part is just the EALF, the equivalent axle load factor, and it equals to linear relation of a set of variables. And also in this equation, you have the definitions of GT and beta X. And if we go to check the definitions from AASHTO, we can see that WTX is the number of the x-axle load application at the end of the time t, and WT18 is the number of the 18 kilopounds single axle load application to the time t, and the LX is the load in kilopounds. So here you have to remember that all the units here is pounds, not Newton. And the Lx is the load in kilopounds on one single axial, or one set of the tandem axials, or one set of the trident axials. And L2 is the axial coat. It would be 1 for the single axial, 2 for the tandem axials, and 3 for the tandem axials. And the Sn is the structure number, and the PT is the terminal serviceability. So once you are provided with these variables, you are able to calculate the value of the load factor. So let me just show you one example about how we're gonna calculate this load factor. So for the in this example, we are provided with the value of PT, the terminal serviceability as 2.5, the structure number as 5, and we want to find out the load factor for 32 kilopounds, 32 kilopounds tandem axial, and 48 kilopounds trident axial load. So let's start with the tandem axial. With tandem axial, we are considering the load of 32 kilopounds. So we have Lx is 32. This is from the definition in the Ashton equivalent factor equations. And for the L2 is in the axial code. It's in the tandem axial, so we have dual tiles. L2 equal to 2. And then we can recall the equation from the Ashton equivalent factor. First of all, we need to calculate the two variables, GT and beta x. For GT, it equals to log 4.2 minus PT divided by 4.2 minus 1.5. So here we know that PT equal to 2.5. So you can calculate the value of GT as minus 0.201. And we can then calculate the value of beta x. Beta x equals to 0.40 plus 0.081 times Lx plus L2 to the power of 3.23, and divided by Sn plus 1 to the power of 5.19 times L2 to the power of 3.23. And in this equation, we are considering the tandem axial. We have Lx equal to 32, L2 equal to 2, while we have Sn equal to 5, and with that we can get the value of beta x for the tandem axial, which will give you the value as 0.470. In this equation, we also need to find out the value of beta 18, which will be the regular one. For the beta 18, we're gonna use the same equation, but here we assume that Lx is 18, which would be the standard axial, and this is also the single axial, so we have L2 equal to 1. And apply this equation, these settings in the equation for beta x, we can get the value of beta 18 as 0.5.